So you should all have this diagram here. Okay, we had our numbers along this side, and then we had our numbers across the top. And from memory, I think our numbers across the top were the blue die, was that right? Yeah. And the green die along the side, okay? So what we did was we put the dots here, and then further than that, we said, well, we were playing Subtracto Bingo. So if you actually roll a 1 and a 1, what would you get? What would the result be? What would you cross out? And the answer was 0. And we followed the pattern across, right? You're gonna get these numbers. If I keep going down, you're gonna get 1, 0, 1, and you guys already have the completed table, all right? So let's pick up now. While I draw the rest of this, I will let you have some time to actually do what I asked you to do yesterday, which is, when you have all of the outcomes laid out there, which you do, and I do not have yet, right? You can work out, well, what's the probability of any of the given scores appearing, okay? What's the probability of getting a 0? What's the probability of getting a 1 or a 2 or a 3 and so on? And then what I'd like you to do is, this is a bit new, I want you to put it into a table for me, okay? So the table is going to have 3 columns, okay? The score, 0 to 5. The theoretical probability, which is what you're about to work out. And then have a think about what we've been looking at over the past few days. What do you think the third column might be? Experiment. Very good. Okay, that redeems the fact that you were slow to get your stuff out. All right. So we're going to fill that out. If you recall, I wrote down most of the numbers, and then different people took over. But we'll just go off my data because I can give us numbers for these. So I want you to fill out this table from 0 to 5. Okay. Under this theoretical probability column, I'd also like you to put it as a percentage. I'll show you how to do that in case you're not sure how. But the reason why is, as you'll see in a second, the fractions are not very easy to compare. Okay, so all of these are going to be percentages for 0, 1, 2, 3, 4, and 5. Just rounded off to 1 percentage. Okay, to nearest 1%. In case maybe you've missed a little bit, or you can't remember how does all these numbers, where do they all come from? Okay, let's start with up here, and then everything will fall from there. 6 out of 36. 6, 36. What do those numbers represent? Yeah.
In the dot diagram, there's 6 zeros.
Fantastic. 1, 2, 3, 4, 5, 6. So in other words, the top of that fraction, every time it's a probability, it's the favorable outcomes, right? And there are 6 of them there, okay? Good. Where does the 36 come from? Yeah, Nathan.
How many possibilities there's left you could pick?
Yeah, fantastic. All the outcomes, right? You count them all up, it's 6 by 6 and it's a square, so that's where we get 36 from, right? Now, when you punch that in, that's equal to 1 over 6, and I think it's 16.6666% or whatever it is, which I'm just rounding off. Okay, so that's where I get this figure from. Okay, I just want percentages to make everything easy to compare. It's usually why we have percentages, all right? So by now, you've gotten a little way through. You should be counting the rest of these. I haven't filled them all out for you, but you'll be able to tell me, and tell me what the percentage is on this next one. Has anyone worked it out already? 27.7, which rounds up to 28, doesn't it? Okay. By the way, just as a note, because we're rounding all of these, right? Notice how this one rounded up, and this one also rounded up. Depending on how these all round, all these black percentage numbers right here, they might not add up to 100%. They might add up to 99 or 101. Just depends on the rounding. Okay. Can someone tell me the next one?
22%.
22. Okay. Now I haven't filled in for the 3, 4, and 5, but you can count up on the dot diagram how many 3s are there.
6.
Yeah, that's very good. Okay, so you got 3 of them here and 3 of them there. Use the symmetry to your advantage. 6 over 36, which we've already worked out, that's going to be 17%. By the way, those wiggly equal signs, they just mean approximately. It's the same as writing an equal sign with dots above and below it. But at least when I'm writing, real whiteboard marker, it's not so bad. But when you're doing it in pen, often the dots, you can't see them. So I think the wiggly signs are a little more obvious. How many 4s are there? 4, very good. It's kind of coincidental. 4 out of 36. That's equal to a 9th, which I think would be 11%, right? And that leaves us with just those 2 5s on the corners. Yeah? 2 out of 36, which is approximately equal to 6, which by the way, you could work out without your calculator because you can look at this and you can say, well, roughly, and then you can do the rounding, right? That should be 5.5 goes up. So 6%. Excellent. Okay. So now you have a look at these numbers. Now, because this is experimental probability, these represent what I actually rolled. Okay, I didn't include some pairs and Connors because it just take me too long to work out the numbers. So I did 52 rolls in total. I think that was 3 rounds, and then other people took over. And these were how many of each number we actually did. All right. So let's get these numbers as percentages really quickly. 10 out of 52. 19. Okay, 13 out of 52, someone in the side of the room. Someone got it already? This is an easy one. 13 out of 52. It's a special number. Do you ever recognize where these numbers come from? This is a common set of numbers in probability. 52, there are 52 weeks in a year, but there are also 52 playing cards in a deck. And there are 4 suits, each of which has 13 cards in it. So because there are 4, you know that's going to be 25%. Yeah, that's right. I heard it, but anyway, that's a number you ought to be able to recognize. 12 out of 52. Any takers? 23. I'm guessing 26. Is that about right? 27? How does it round?
27.
27? And then these numbers here are going to be very small, aren't they? 4%? Good, which we'd expect because it's half. Okay, now I just want you to have a look at this table now that it's complete. You can see that there are quite a few discrepancies, aren't there? Right? Some of the numbers, very, very close. Look at this. 17 versus 19. 28 versus 25. This one is within 1%. 22 versus 23. Okay? But these other numbers, they're kind of thrown off, aren't they? Because we just happen to get a lot more 3s than we should have expected. That's why these are a lot lower than also what we expected, which is why you guys kept on saying, come on, why are we getting 4s or 5s? Actually, we should have probably got more 4s or 5s than we really got. Okay. Now, I'm going to replay this scenario again. I wonder if you've still got your sheet there, and if you've used up all of the rounds. Okay. We can use this to design, in theory, the perfect card. Right? There are 12 spots to fill. 12. Okay. So being that, see this column here, this one? This is what is supposed to happen. It doesn't always happen, but this is, in theory, what should happen. Okay. So on the basis of this middle column, what would the perfect card look like? I've got 12 spots to fill. Okay. How many, for instance, how many zeros should there be in my 12 spots? How would we go about calculating it based on that column? Well, we predicted 17% of our rolls should end up with a 0, right? So
2 zeros.
2 zeros. Okay, now where did you get the number 2 from?
I got 4 3s, 3 1s, 3 2s, and 2 zeros.
Okay, so was that, but where did you get that from? Those are the numbers. Where did they come from?
The highest amount should be the highest percentage.
Okay, good. So the first thing we should say is, look, see what this one, we predict it should be 28%. Look how many 1s there are. It's clearly going to be the most common. And it was. No, it wasn't. That was weird. Okay. But we should have the most 1s. But I'm not just curious about, I want the most 1s. I want to know how many 1s there should be, because they're not all going to be 1s, right? So let me come back to the zeros. That was the first question I asked. I predict 17% of my rolls should end up as a 0. So therefore, I should predict that 17% of my 12 will end up as zeros, right? 17% of them. So what's 17% of 12? Well, it's actually, if we go back to exact, it's a sixth, right? So it's exactly 2, right? So we should predict for the zeros, right? We should predict 2 of them, okay? For the 1s, how many should we predict? We should predict 28%, right? What is 8%? It's not going to be a neat number.
3.36.
3.36. Okay, so that's going to round down. So I'm expecting 3, right? But there's still quite a decent chance that it could go up, right? And you can continue this, right? For 2, 3, 4, and 5. Go ahead and do that. design the perfect card. Tell me how many I'm going to get for each of these numbers. Okay, so let's have a look here. 2, 5, 8, 12. Perfect. And this should be our perfect card in theory, right? 0, 0, 1, 1, 1, 2, 2, 2, 3, 3, 4, 5. That's it. Okay. All right. Now let me follow with one final question before we end on this. Okay. That's the perfect card. That's the ideal card. But if you have a look at the people, for anyone who won, anyone who actually won, I want you to compare your winning card. I know not everyone has a winner, sorry. But those of you who do, sometimes more than one, will be different to this card, right? Your card won't match this card. That's the first thing. The second thing is, this card won't always win, even though it's the, inverted commas, the perfect card.